Hello friends, now we are continuing with the series of videos on HPZ and cuda, and this video we are going to talk about a new concept. This is called a matrix multiplication using 2D indexing. So far we were discussing about 1D indexing, now we will discuss about 2D indexing. As you can see on the screen, matrices are 2D arrays or numbers or symbols or expressions arranged in rows and columns. We know that, and these are very much used in every field of physics and engineering. Up till now we were indexing 1D arrays, but now we will be indexing 2D arrays. In cuda, matrices are passed as arrays, but they are indexed as matrices. Now it is always, we know that in matrices rows are multiplied by columns. So accordingly we have to do 2D indexing. Now if you remember, in 1D indexing is like the threads were from left to right. If you see in different blocks, they can be conventionally written as 0, 0, 1, 0, 2, 0 in every block. So 0, 0, 1, 0, 2, 0 is like when we write in rows and columns, it is 0th row and 0th column, and first row and first 0th column, like that. But you make it opposite to that, rows and columns you invert it, so it looks like, so it will be 0th row and first column, 0th column, row and second column, like that. So whatever is written, it is an inverted form, is the row column format. So whatever it is, so this is how you can index it actually in the XY format. Now look at this structure where we have a grid. Inside grid we have blocks, and inside blocks we have threads. Take one block 1 1. You have multiple threads. Let's say 1 2 3 4 4 into 3, 12 threads inside. So you can reference it by XY method, XY indexing. Now more complicatedly, we can, as I said, grid, under grid we have blocks, under blocks we have threads. So we can even reference each thread in a 3D format which looks like this, where we will have the individual bricks are the threads actually. So that is also possible. Now when we launch a kernel, we have to be indexing it correctly so that we will be able to get the matrix form of indexing. Here we will focus on an indexing method which looks like this. See, for example, dim3 block dim 2 comma 2, that means we are trying to put 2 rows and 2 columns. So it will be total 4 elements, and dim3 is a data type, and one is for the block dimension, other is the grid dimension. So in grid dimension, you can, like in earlier videos you must have seen, it was n plus m minus 1 divided by m. The same thing is replaced, m is replaced by block dim dot x. So instead of m, it is block dim dot x, something like that. And same way here, you see the difference is here you have x and y, and by doing this we are defining a block containing 2 threads in horizontal direction and through 2 threads in vertical direction. So pictorially you can express it like this. It's very simple: 2 threads in y, 2 threads in x. Now indexing is done earlier we were having an indexing, index I, that was having symbol format. Now we are having a block IDX in Y direction dot Y, that block div dot Y plus thread IDX dot Y. For integer IY, it is block IDX dot X multiplied by block div dot X thread IDX dot X, something like that. So ultimately you have to, in matrix multiplication, you have to multiply rows by columns. So that can be achieved using this particular formula. Now let's get into the program. The program is exactly like earlier, but the difference is here indexing. You have to index IX and IY, which was explained earlier. Now we can say that how do you create a sum? Sum is created using this particular formula through this indexing. That means rows and columns are added together. And now whatever results are there, actually it will compensate in the C array. So the main program is n is equal to 2. That means this is like matrix dimension of n into 2 by 2. This is right now we have explained everything for square matrix only. And if we multiply all this, and similar way you allocate the memories, etc., then the only thing is here you have to define a grid and block dimensions actually using the data type div3, and this is something which is extra from earlier programs. So then other things remain almost same as earlier, and when you execute this program, you will be able to get into the profiling part. Actually we will practically demonstrate it actually a bit. So now you can see this particular program, we are getting into the HPC and we are running that program using srun minus n, then 1, then minus p, GPU is equal to 2, GPU column 2. So this is how you start with. And after this you can see the sq command to see the user. Sq minus u $user will give you the node allocated. This is the RPGPU3. Then you have to do SPAC is one you have to use for loading the softwares. So you cannot paste the environment, and after that you say load cuda. This is the version name, and you also need to add a string after this. A string will be got from the top. Now it's the time to run the program. Now we can first see the program once, whatever we were discussing. So this was matrix multiplication underscore using shared memory. So here in this particular case, so it is not only doing the matrix multiplication, but it's also using the shared memory, which we discussed in the last video. Now we can execute this program. After executing this program through NBCC, you can see the output, and once if we verify the output, which is copied 2 by 2 multiplied by 2 by 2 will be again 2 by 2 matrix only, and after that you can do a profiling using this So for this you have to create a report, which you have done. Now you simply drag the report file into this. How much time it took? It only took 2.2327 microsecond. That's all in this video. See you.